So luminescence is going to be the term that we use to describe two different processes at once. We can refer to fluorescence as a form of luminescence, and we can also refer to phosphorescence as a form of luminescence. In both of these cases, what we're going to do is we're going to put some energy into our molecule by having it absorb a photon. Some of that energy is going to be converted into heat. See that being shown here with our arrow up, and then our wiggly process down. That's showing that it's a heat deposition. Two possible fates for the molecule become fluorescence, where we emit a photon, and there's probably going to be some thermal levels down here that it can relax to as well, which means we're going to have a range of energies being emitted, and they're all going to be lower in energy than we had originally. Now, of course, if it's lower in energy, that means it's going to be further toward the red end of the spectrum than it was toward the blue end of the spectrum. So if this is a violet photon, this might be a green photon coming back out. We can do an inter-system crossing to a triplet state, which means that our electron has flipped its spin, and now it's being parked up here, and it lasts for a really long time in this state because there's actually a physical restriction from it coming back down, namely that if we have it originally in an upspin here, and it was paired up with another electron in the downspin, and we promote this electron up, it'll still be an upspin here. When it relaxes here, no big deal. It just drops right back down and it's still spin paired. When it converts to a triplet state, the spin flips, so it becomes a downspin. We still have a downspin underneath in the ground state. These are on different levels, so that's not violating our exclusion principle. But as soon as it drops down, right now we'd end up having two downspins in the same orbital. They would have the exact same quantum numbers, and so that's forbidden. We can't have that happen. It's going to be parked up here in this excited triplet state until finally it can get around to flipping its spin again and dropping down. Fluorescence will be a reasonably fast process. We're talking about 10 nanoseconds out to hundreds of microseconds. And then here we're talking for phosphorescence, we're in the microsecond to minutes regime for phosphorescence most of the time. Now, of course, you may have some even faster or even slower fluorescent processes, and you may have some much longer-lived phosphorescence as well, but these are the typical ones. Now, when we see that, we said that we'd expect our spectrum to be further toward the red end, and sure enough, we see that here. And they actually did something kind of neat here. They used a camera flash to excite the molecules, and then they used two different filters to select whether they're going to do fluorescence or phosphorescence as part of their experiment. Just kind of a neat little side note. So they were selecting something more toward the blue end. They pumped it in, they got their fluorescence out, but notice that we specified here phosphorescence was being done under fairly cold conditions. In other words, we wanted to actually do a little bit of thermal trapping. We wanted to slow down how much heat energy was around and kind of trap it here to have this longer lived so that we'd actually see more molecules end up going the whole way through into phosphorescence instead of just thermally relaxing. So keep in mind that we've had to amplify this 10x in order for it to be very visible. So in reality, if we want it to be on the same axis, the intensity is going to look kind of like this compared to what you see for the fluorescence profile. And that's still after we've actually cooled it down so much that we can get it amplified enough to be on scale at all and observable. Okay, so that's going to be our luminescence processes. We're going to have it in a separate video how exactly we'd go about doing a luminescence measurement.